It's my pleasure to introduce Dr. Michael Titus. If I talk long enough, people will kind of settle down. Okay. Um, so it's my pleasure to introduce Professor Michael Titus. Dr. Titus joined us at Purdue after, I think you had a Big Ten beginning-ish, right? So he went to a school that starts with the in its title, the Ohio State University. Um, got interested in materials through engineering physics, right? And went to University of California, Santa Barbara, proving that you can do really good work with pretty scenery and beaches and a laid back attitude and a horrendous cost of living, which we like to think helped make Purdue attractive for coming back to the Midwest. Mike, when he interviewed here, was able to, he was toying between whether, he had this Humboldt fellowship pending. He was going to go off to Germany, maybe. And we were lucky enough to be able to have an opportunity to talk with him and get excited about what he was doing because, our bumper stickers say you can't make it without materials. That's not my line. That's 3 heads ago. And Mike epitomizes the making of materials. So what he does is he makes new materials. He has new ways of treating materials. The alloys he works on are the type of materials that end up being on the Mars rover when Haynes has, hey, our alloy went off and guess what landed on Mars? Well, people like Mike have a hand in making that. So you can't make it without materials. You can't make devices. You can't make products. You can't make things if you don't have the stuff you make things out of. So Mike interviewed. We recognized this was going to be a really outstanding opportunity, and we were able, and this is the advantage of being at Purdue, have the comfort to say, hey, if you get the Humboldt, go to Germany, because what, you're going to get worse? No. So he had a great opportunity and came back and hit the ground running. And I assume what you will see is a little bit about how you get through that. If I'd known the previous question and answer, I would have tried to work in a joke about metal or something and musical things. But with that, I will just turn it over to Professor Titus and say thank you very much.
All right. Thanks, Dave. Yeah, so today, beyond, I guess, my career path, I'll be talking a little bit about hot metals and fast planes, which are my 2, I guess, professional interests. So for the aero folks in the room, this may be a bit of a controversial statement, but the F-15 is the coolest fighter jet, and you cannot convince me otherwise. At least that's what I thought as a kid. And so this was by and far, in a way, my favorite fighter jet when I was a kid. It has some interesting stats. So it had the world record altitude climb record at some point, so 100,000 feet in 3.5 minutes. That's pretty crazy. It's the only plane to shoot down a satellite, also pretty crazy. And its air-to-air capabilities, it's 100 kills to 0, right? And so it's probably one of the last fighter jets to actually have real dogfights out there. So what got me interested, though, is these engines. So this is the GEF 110 turbofan engine. Some stats, you can take my super alloys course to learn more about these and materials, but 17,000 pounds of thrust dry and 29,000 afterburning, 31-to-1 overpressure ratio. So we're increasing the pressure inside that engine 31 times over the atmosphere. And the crazy thing to me is that the hot combustion gas operates at 1,500 degrees Celsius, but the metals that extract the energy from that melt at 1,300 C. How does that even work? So we'll talk about that here in a minute. So things like that started to get me really interested in metals and fighter jets and aviation, etc. Well, being from Cincinnati, Ohio, I had ample opportunity to get involved in this stuff. My dad and my grandfather, shown on the right, worked at GE Aviation for their entire career, increasing rarity nowadays. And, so I was interested in engineering, maybe some aviation, not really sure. So I wanted to pursue a more broad degree in engineering physics at The Ohio State University. Sorry for the typo there. And during my process there and earning my BS, I took 2 internships at GE Aviation, now GE Aerospace, thanks in part due to my family friend Walt Buttrell, who got my resume to the right person. Always use your personal connections whenever you can, because finding a space for an engineering physics major at GE Aviation is pretty tough. So that was kind of the through line there. So being at GE Aviation got me really interested in the high temperature metals that are used in these gas turbine engines. And so I wanted to pursue my PhD in materials. And my advisor was Teresa Pollock then. So, I went into my PhD actually even before that, thinking I would just go work for GE, be 25 with a house and family, and, the stock market crashed, so that didn't happen. And so, going into my PhD, I didn't really know what a professor was. That wasn't even a viable career opportunity for me. And so while I was working on my PhD, I enjoyed writing papers, I enjoyed traveling, enjoyed giving presentations. And so I started to think, well, maybe, I should start to look for these faculty positions. An opportunity opened to attend a future faculty workshop at Purdue. So if you're interested in being a professor, students try to seek out these opportunities. I applied in my final year and accepted a position before I went off to do a postdoc in in DE, Deutschland in Germany, out at the Max Planck Institute for Iron Research. And also there, I have to say, I met my wife, Anna, who's here in the front. That's back when I actually had a motorcycle and rode it. Weather here isn't all that great. I learned a lot about how to work on engines as well with these motorcycles, which, was one of the reasons why I bought a motorcycle, right? Just to learn how the engine works, of course. So there's this hiking. One really interesting morning, I remember at 3 a.m., I just happened to look at a Twitter notification that came by when looking at what time it was. Shuji Nakamura won the Nobel Prize while I was there. So that was literally a circus in the morning at UCSB. And that's a picture from my phone of basically that press release when he won it. So that was a really unique opportunity. So after my postdoc in Germany, I started at Purdue in December 2016, and yada, 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 came to a sabbatical now at Imdea Materials in Spain, and then now in the future will be spending a month in the Karlsruhe Institute of Technology. Just like to say, this is during our sabbatical. This is our daughter that we welcomed last year while we were in Spain on sabbatical. How do you call that? Chulapa. So very cool girl, I guess, is the literal translation there. So more traditional Madrid dress there. And then my family was able to visit us as well. And then my in-laws are shown there at the bottom, and they hosted us, and I'm very grateful for them for the time that we were able to spend with them this past year. So I work on metals, and one thing I really like to get across to students is that I think, if you do a Google image search, this is what you see, kind of really red hot metals pouring and kind of dirty, the soot on that guy's face. And, if you're interested in metals, this is a career that you can pursue, and many of our students do pursue this. But nowadays, it looks very different. So here's, some of the laboratories that we're working in. I point out in the top right, this is a transmission electron microscope where we thin down metals to 100 nanometers, sometimes even 20 nanometers, right? And so it's only a few atoms thick, essentially. And then we just stick it in this microscope and crank up the magnification to see atoms, and I'll show you some of that later. So it's very different metallurgy now than perhaps what you may have considered in the past. And metals are everywhere, right? So I remember when the Ford F-150 changed from a steel chassis to aluminum, GM came out with a commercial making fun of them for their weak aluminum alloy. And then 2 years later, GM started moving all their trucks to aluminum as well. So that saved a ton of weight for Ford and now GM. Aluminum at the time was used on that iPhone Model 5S, I believe, and now Apple spent a bunch of time trying to figure out how to make it out of titanium, which is a really interesting metal story in that own regard. Advanced electrical steels, and then, of course, at Purdue, we're interested in hypersonic vehicles, and metals are used there. And the titanium skin enabled the SR-71, the Blackbird, which is my second favorite plane. And so to kind of summarize this plane, and what's really interesting is that the skin on this plane got so hot during flight operations, they needed a new alloy to cover it with. So they co-designed a titanium alloy during the development of this plane. And honestly, a lot of that co-design for a given application has kind of been lost because we've come up with this whole catalog of materials that designers can go pick and choose. And then they say, okay, that one will work. And, I'll design around the deficiencies in the material properties. But nowadays, I think we can come back to this concept of making new materials specifically for an application and making that co-design process very successful as it was for the SR-71. Well, very successful. They did have problems. It heated up so much that the titanium alloy aged and brittled. And so when they were doing repair operations, they would just often break off many of these rivets, and a lot of the tooling would just get completely destroyed. So, they didn't know everything about titanium at that point, but, it flew. So good enough, I guess. So my research works a lot on high temperature metals used in gas turbine engines. And so in particular, these are the engine components that are near the aft, the highest pressure, highest temperature capability structural materials out there. At least they have the nice balance of properties. This is a high pressure turbine blade. It's coated with a ceramic coating and has complex internal cooling passages. It's frankly a marvel that we can even make these things and that they can survive 1500 degrees C when they melt at 1300 degrees C. These individual blades that are about this big have to support on a 3 millimeter cross section the weight of a F-150 at 1000 degrees C. So it is truly remarkable what these metals are able to achieve. I'll skip this real quick. Again, just to say things get really hot in these turbine engines. But what makes these materials withstand the heat are these thermal barrier coatings, these ceramic coatings that are about the width of a human hair. So that's that top thermal barrier coating you see there. And these active cooling passageways. And these are cast components that are, again, very difficult to create during these casting processes. These superalloys are also very complex. So, you can look from these very large land-based gas turbine engine blades that are about 3 feet long to aero-based ones that are, a few inches long. Looking closer, you get this called dendritic structure with some inhomogeneities there. This, at an even finer length scale, actually provides that high temperature strength. It's kind of this brick and mortar-like structure. In my group, I'm really interested in looking even at smaller length scales. So these little black lines are not actually in the material per se, but it's just due to the diffraction conditions that are used in these transmission electron microscopes that I mentioned before. But these are called dislocations. They were theorized many decades before they were actually observed, as I'm showing in this image from my PhD thesis. And we look all the way down to the atomic structure. So each one of these dots here is a single column of atoms. And you can see that kind of in the middle, there's an interruption in that stacking sequence. And we're interested in modeling the change in chemistry there through atomistic simulations, but also verifying them as well through experiments. And we relate these two all the way to the left, the macroscopic behavior of these metals. So a lot of this work from my thesis work shown on the left, looking at these atoms basically, formed the basis for my NSF career that I won here when I got to Purdue. And so I really have to kind of shout out Dongsheng Wen, who's now a postdoc in the UK. And he really worked on the theory of this. And one thing that I want to kind of get across to the graduate students here is that we're citing work from 1952 and 66. So again, this phenomenon was theorized well before anyone could actually characterize it, and well before we had the models to actually predict the behavior of the composition variations. And so we basically take new toys and apply them to these very old theories. So when you're in the library, don't be afraid to look up really old papers, because there were just as smart people then as there are now. So definitely utilize those. So we've also looked at shape memory alloys as well. On the left, it's a pretty unique material where you can bend it, deform it, put it in some hot water, and it will go back to its original shape. This was with my colleague, Professor Strachan here. Here we're looking at novel materials that are magnesium scandium or magnesium lithium based, and we're trying to basically make them better for higher temperature applications. And this was a nice example of that. More recently, we've been looking at discovering and also designing materials for high temperature applications. This is again with Professor Strachan, Ali Strachan, Ilias Bilionis, and Emmy, and Ken Sandage, who's here as well, where we're trying to discover very strong and oxidation resistant materials here using a combination of machine learning and autonomous discovery of new materials. And then I also had a nice collaboration with AFRL for a couple years where we were looking at oxidation properties, and my group was doing the modeling for this work. Nice pretty colors here of these various oxide layers that are forming, and we tried to model this that we've then applied to other systems as well. And then finally, just a little vignette here again. This is with Haynes International, the company that Dave mentioned that has produced material that is on Mars right now. Or that got the rovers to Mars. So here we use a combination of atomistic simulations with phase field dislocation dynamics with Professor Marisol Kozlovsky to determine how these materials deform under extreme conditions. And so this was a very, again, a very nice example of this. On the far right, I'd say my current PhD student, Victoria Tucker, was able to get this image. It may be, in my mind, the most beautiful high-resolution TM image that I've seen, eclipsing what I got for my thesis. So I'm envious of her work on that, and she's worked very hard to achieve that. Oh, and during this work, we went to the beamline and we took a little trike ride around, the multi-mile synchrotron ring up in Argonne in Chicago. So more recently, though, we've been taking these fundamental studies and applying them to our various industry consortia that we've spun up in materials engineering in the past years. So one in surface engineering and enhancement, heat treating, which I've been leading with Mark Runninger, and then our new Center for Metal Casting. And it's really interesting to take the fundamental part of our work and apply them to what's important in industry to actually make stuff and make it relevant for things that you all use on a daily basis. And this is really enriched and kind of refocused some of my research to be more useful and a little bit less fundamental, but we still pursue these two tracks in parallel. And so here's some of the industry members that we have in these. And this has been a really great opportunity to work with folks from around the Midwest, as well as some old colleagues from General Electric, actually from when I worked there about 15 years ago as well. And so I have to, of course, give thanks to my current group who's working on a variety of projects, many of whom are co-advised by others here like Ken Sandage, Tim Pourpoint. I'm not sure if I'm missing anyone else right now. And so we have a lot of exciting projects going on currently. And of course, I need to acknowledge many of my faculty mentors, mentees, and staff, Purdue friends and family. I can't go through all of them, but to point out a few, my PhD advisor, Teresa Pollack, and Dave Barr, both of whom have been very close mentors and helping me throughout my career in various stages. Xingang Zhang and Alejandro Strachan as well, the formal mentors, many of my co-PIs, et cetera. And the staff as well has been amazing to keep me up to date on business things, and as Chris said, make sure you're where you need to be at various points. I also need to point out my family. So my wife, Anna, of course, very happy that she's here with me in the States, far away from her family, but we got to spend a year in Madrid with her father and mother, Pili and Javier, and her brother and sister, also Pili and Javier, because as I make the joke, everyone in Spain is just, they have the same name. So So for my PhD thesis, I put a PhD thesis by the numbers. So here's some good outcomes from my time as assistant professor. 4 MS and PhD students graduated, a few awards, a lot of conference symposia organized, some funding, et cetera. One thing I really want to point out is I've been really involved in faculty mentor and service positions, both in and outside of the department. And that's been really rewarding for myself. A lot of times, many professors like to share only the good things, but it's also a process of learning, and you have to have kind of thick skin as a professor. So here's some undesirable outcomes. 2 to 3 years of imposter syndrome early on. That was a bit uncomfortable, and so that's since been overcome and feel much better in that regard. A few rejected manuscripts from journals. It happens for various reasons. Sometimes a reviewer is really silly. Other times your work probably doesn't deserve to be in that journal and you just have to accept it. Some significant awards rejected, 7 rejected PI full proposals, 31 business trips. I used to really like travel, and now airports sometimes just feel a bit like a jail in a way. And 110 days on travel, and remember this was during COVID as well, so that's really only over 4 years or so. So it's a fair amount of time on the road. For students, I would encourage you to get involved in your professional societies. This has been really enriching for me and has led me to be appointed to the board of directors for a 14,000 member TMS professional society in just a few short years. It started with a scholarship, being involved in a organizing committee, and then a few other appointments and awards. And now I've been working on the public and governmental affairs committee, where we're interested in public outreach and advocacy to the federal government. One thing that we've really been focusing on is ramping up production of raw materials and mining in the United States, because that titanium I mentioned on the SR-71, 70% of it came from Russia before the war with Ukraine and the invasion in Ukraine. And now, a lot of companies are struggling just to get titanium. We need to increase that industrial base here in the United States for titanium and other critical materials. So I mentioned some service and outreach. We've been able to actually cast some Purdue branded, so to speak, medallions for K through 12 students, both at Klondike Elementary, as well as on the mall for our homecoming activities. And then Akul Seshadri is up there, is pounding away at some 52-100 steel for a bladesmithing competition that our students are involved in annually, where they make these nice blades that are not sharp, and they're judged on their metallography and metals expertise in that area. So what are the next steps? What are the things that I'm looking forward to in my career? There's been a large push, and I'm on board for autonomous labs for materials discovery. We can make maybe 40 alloys in the span of, I don't know, a couple months to a year or so. Can we make 1,000 new materials in a day? That's what we're interested in getting to in the future. But also, I go back to the idea of the co-design. So can we make new materials and new rocket designs at the same time to fly them? And the same with rotation detonation engines as well. And I just got a tour of the Z09 labs, which is very nice. Unfortunately, I wish this image showed the business end of the building where it's all being tested at, right? So I want to help make some of these new materials, test them, and hopefully fly them. And I think literally only at Purdue do we have the opportunity to do this across the country. And so that's one reason why I'm here today and accepted that position many years ago. So with that, thank you very much for your time and attention, and I can take any questions. Thanks.
So we have a mic for questions. We have questions for Professor Titus. Somebody has to start. And I mean, I can do one, but it'd be a lot more interesting if it was from somebody else.
Can you explain why you feel an F-15 is better than an SR-71?
Then what?
Than an SR-71. I mean, the profile.
Yeah.
I struggle with that.
Yeah. Well, I'm a bit biased for the F-15. One of my really good childhood friends, his father was an F-15 pilot. So come on, he was, coolest guy I knew, right? But I don't know. Just going to an air show, not many SR-71s you see flying, obviously, because they weren't flying at the time. But man, those F-15s, when they just crank on the afterburner and just go straight up, it's just like, yeah, I want to be that. And I did. But for various reasons, didn't go into the Air Force. So yeah, I would have loved to see an SR-71. If you want to read more about it, there's this book called Skunk Works, and there's a story of a pilot buzzing the head of Skunk Works on his house in Santa Barbara, relating it back to my time there. That would have had to have been incredible. The turning radius at Mach 3 point something something was basically the size of the United States. Right, so they would just go into a left turn bank over Seattle and come back over San Diego. That's how fast this thing was flying. Incredible plane too.
Where was your advisor from? Where did she do her undergrad?
Yeah. So where did my so let me go back another step. So my advisor, like many metallurgists, are from Ohio. So I have a working theory that if you're going to be a good metallurgist, you need to be from Ohio. So there's a lot of us, as it turns out. And so, but she actually, that's another point I want to bring up. So she went to Purdue for her undergrad. And so she came back a few years ago for the Purdue Engineering Distinguished Lectureship, which was really great to have her back. But also like Purdue for me as an undergrad, in a way, someone like Chris was mentioning, I didn't have the grades to get into Purdue when I was a high school student. It wasn't until I got really focused in physics and materials engineering that I kind of found my path. And so to me, it was a huge accomplishment to get a position at Purdue as a faculty member. That was literally not even in my dreams at the time. So yeah, it's just kind of funny how that comes around. And the nice thing about being a professor, you can work on the research that makes you excited, right? And that's one of the reasons I think why many of us have this job.
Mike, can you hear me? Yeah, okay. Well, first, well done on successfully navigating the Van Halen question. In this case, SR-71 versus F-15. A lot of buzz in the background. What? That was great. And to the point of Dave's earlier point of making sure there was a pun, I congratulate you on your medal to go over, all the challenges in getting rejected in your initial proposals and so on. But something you alluded to, which is this, the space of superalloys. I'm not in the area, but I find it absolutely fascinating. In fact, Dave and I have spoken also, like so many superalloys remain to be discovered, right? It's like this is the tip of the iceberg where we are, right? And to some extent, coming up with 1,000 per day is probably, even that remains scratching the surface. So the question is about in the future, what could we do to become how does one really use AI, ML at scale? How can one do that to discover new superalloys? There's a smart way of doing it, but the scale of it goes up, the computational cost goes up exponentially to find the right ones for the right so what's a smart way that might help us become the place for superalloy discovery?
So it's even beyond superalloys. So we've been working a lot on refractory alloys that melt above 2000 degrees C, and that's even a subset. But if you broaden it to literally any material out there on the periodic table, any condensed matter phase, I'll say, there's been some estimates that you can come up with 14 billion compositions, right? And it is literally infinite, but practically 14 billion seems to be a good upper limit. So if I tell my PhD students, go make me 14 billion compositions, they're never going to join my group. So it's exactly that. How do we find smarter ways to get through it? So we do two things. So we do high throughput, cheap calculations to just kind of understand the broader space, and we can filter and down select by about an order of magnitude, sometimes 2, from our initial design space. And then after that, on a project that we have Ken Sandage here, we have right now 7,000 alloys that we could potentially make, still too many. So we use machine learning to better predict the properties and understand the uncertainty in those predictions as well. And that's what I've really learned a lot from Professor Strachan and Billy Onis in that regard is how do you choose the next material to go make? And there's ways that you can do it very efficiently. And we've shown that in the paper that we've just submitted, where instead, finding, let's say, the highest strength material in 7,000 alloys, and you go make 7,000, we did it in about 40, right? And so you can greatly reduce the amount of time and cost necessary to find that. And it's through basically uncertainty quantification in the predictions of your material properties that get you there. And that's the big one. So.
Every combination.
Phase transition diagrams, phase diagrams, basically that's what we're doing. So we can run, it takes us about like a second or 2 seconds for every composition, but thanks to the massive clusters we have here, we can do hundreds of thousands per day. So so they're fast, yeah. parallelizing.
So I think to stay on time and to honor your trips, on behalf of all of us, Danke, gracias. Did I get that right?
Gracias.
Okay. So thank you very much, Mike.